Hello. In this video I'm going to be going through this problem here. So I'll first read it out to you. Point A moves uniformly with velocity v so that the vector v is continually aimed at point B, which in its turn moves rectilinearly and uniformly with velocity u, which is smaller than v, and these are velocity magnitudes. At the initial moment of time, vector v is perpendicular to vector u, and the points are separated by a distance L. How soon will the points converge? Okay, so the first thing to note about this question is that there is no gravity involved in this question. So that means it could be maybe set in space, so deep in space where there's no gravity, or it could be set even in a 3D plane but just there's no gravity present, so that makes it a bit simpler. And because it says that point B moves rectilinearly and uniformly with velocity u, that means point B is moving in a straight line, so we could reduce this whole problem to something that's happening in a 2D plane. So that's all we need. So I'll first draw that 2D plane. So we can use an XY plane. But here, X and Y, they don't necessarily mean horizontal and vertical. They're just perpendicular to each other. So this is the X direction and this is the Y direction. And I'm going to say that point B is over here and it's going to be moving rectilinearly, so in a straight line, along the Y direction. So I'm going to draw it like that. And so that's, and point B is travelling with a velocity of u. So this is vector u. Okay, and it told us that initially point A, which is a distance of L away from point B, it was travelling with a velocity of v, which is perpendicular to vector u. So I'm going to say my point A is over here. There's point A, and this is point B. And initially point A was moving perpendicular to vector u, so like that, and that's vector v. Now if point B wasn't moving and point B just stayed there, because the question tells us that point A is continually aimed at point B, we know that if point B wasn't moving, point A would just move along this line here for a certain time until it reached point B. But that's not what's happening here, because point B is moving as well with a velocity of u. So we know that point A is going to go something like this. It's not going to be in a straight line, so it's going to be moving in more of a curve. So the trajectory of point A is going to look something like this. And it's going to meet point B at a certain point. And the question is asking us to work out how long that's going to take. So how soon will the points converge? Also notice that there is an angle between the vectors v and u, which is continuously changing. So if I bring the vector u over here, we can see that initially the angle between u and v was 90 degrees, but as A moves in a curve and vector v is changing direction, the angle between them, so if I call the angle theta, the angle between vector u and vector v is continuously changing. So theta is time dependent, it's a variable of time. And the question tells us that initially the points were separated by a distance L, so I'll just label L here. That's the distance between A and B. Now, just bear in mind that this diagram here is drawn from the frame of reference of a stationary observer. So a stationary observer would see that point A is moving in this curved trajectory. But in order to solve this question, we're going to need to think from the frame of reference of point A. And if we were in the frame of reference of point A, what we would see is point B moving towards us with a certain velocity. And in order to work out that velocity, we need to take a component of u, this vector u, in the same direction as vector v. So I can draw a diagram to show how we can do that. So again, if here we have point A and we have the vector u, and at some point, so vector v is going to be like that, and the angle theta in between them is still there. And if you want to take a component of u in the direction of v, so this is v, and we want to take a component of u in the direction of v, we can draw a line there, and we can see that the component of u in the direction of v is equal to u cos theta. So that component there is u cos theta. And because we are doing relative velocity, we're doing the velocity of point B with respect to point A, we need to subtract A's own velocity from this. So the relative velocity of point B with respect to point A is equal to u cos theta minus v. And here we don't really need the vector signs, but it's fine. So now I'm going to introduce another variable, and that's the distance between A and B, because if we are going from A's frame of reference, the only thing that point A can measure is the distance between A and B. So if I just take any point, so for example, when A is here and B is say over here, now this is kind of arbitrary, just imagine that this is a certain point in time, then the distance between these 2 points I'm going to call that distance r, so that's just the variable r. And so any change in this variable r in a time of dt, that is going to be equal to the velocity, the instantaneous velocity of point B with respect to point A. So I can write dr dt is equal to the velocity of point B with respect to point A. So it's equal to u cos theta minus v. And now that I have this, I can do some things with this. So if I rearrange that to dr equals u cos theta minus v dt. Now I can integrate this equation. So first I need to decide what limits I'm going to use. And so we know that r, our variable r, initially, so r is the distance between the points A and B, and we know initially that distance was equal to L, the initial distance between A and B. But at the point when A and B collide, we know that the distance between them is going to be 0. So our lower limit is going to be L, and our upper limit is going to be 0. So dr, lower limit L and upper limit 0, is equal to so dr integration L to 0 is equal to integration u cos theta minus v dt, and initially t, so at time t equals 0, so from 0 up to some unknown time, so that's the time it takes for the 2 points to collide, so I'm going to call that capital T. And now I can integrate this. So on the left hand side I'm going to just have r from L to 0, and on the right hand side I'm going to have u integration cos theta. Now notice I can't integrate theta at this moment because there is a relationship between theta and t, because theta is time dependent. We can see here that theta is changing as a moves in this curved trajectory, but I don't know the exact relationship between theta and t, so I just leave that inside the integration. So it's 0 to t, and v is a constant, so that would just be vt from 0 to capital T. And if I take this further, I have minus L equals u cos theta dt 0 to t minus vt, which is equal to L equals vt minus u integration cos theta dt 0 to t. Okay, so this is one very important equation that we have. So I'll just put a box around that. But we still don't know what this part is equal to, because we don't know the exact relationship between theta and t. However, we do know that when the 2 points eventually collide, we know that the distance travelled by point A in the direction of u, so in the y direction, that distance is going to be equal to the distance travelled by B in the y direction. Well, B only moves in the y direction, so the distance moved by A in the y direction is equal to the distance moved by B. And we can work out what this distance is because the velocity of point B is constant. So, and we know the time taken for this collision to happen. We've said it's our capital T. So the distance that point B travels is equal to ut. So ut. But we also know, so we can write that for point A, it's moving in the y direction, so we can say that a change in point A's position in the y direction, so that's equal to dy in a specific time dt, that is equal to a component of point A's velocity v. So if I draw another diagram here to show that component. So again, here's point A. Here is the vector u. And at this certain point we're saying that v is like this. And the angle between them, theta. And if we take a component of v in the direction of u, so in the y direction, if we draw a triangle there, we can see that the component of v in this direction is equal to v cos theta. So this component here is equal to v cos theta. So we can write dy dt is equal to v cos theta. And if we rearrange this equation, and we integrate it and put in the limits, we know that y is going to start off as 0 because initially at point A it hadn't moved any distance, so 0, and its upper limit is going to be equal to ut because it moves the same distance as point B. So this ut is the upper limit. So 0 to ut. And on the right hand side, it's going to start off from t equals 0 and get up to that capital T. So the time it takes for the 2 points to collide. So we have ut equals v is a constant, so we can take that out. So v cos theta dt 0 to t. And we can rearrange this so we get the value of integration cos theta dt. So integration 0 to t cos theta dt is equal to ut over v. And this is our second important equation. And what we can do is simply substitute in this equation into our previous equation, because we now have the value of integration cos theta dt, and we can put it in there. So we have L equals, so remember L is equal to Vt minus U integration cos theta dt, so it equals Vt minus, it will be U squared T over V. And now we can just rearrange this to get the value of T. Right, that's a capital T. So we have LV equals V squared T minus U squared T. So T is equal to LV over V squared minus U squared. Yeah, and that's the final answer.